Welcome back. And the topic today is a continuation and wrap up of the electron gas calculations. And I will also point to things which we will have in the exercise next week. So I just wanted to repeat some of the calculational ingredients which we dealt with in computing the energy for the electron gas. And then after that, we are going to make a link with density functional theory and Hartree-Fock theory. So we will not in this course, because we have a parallel course at the university, which actually focuses on density functional theory, which two of you are following. I will just focus on the links between density functional theory and mean field theory, and how we can use the results from the electron gas in the calculations of single particle states and density functional theory. So there are some technicalities which I also need to introduce, like the density matrix, one-body densities and quantities like that, which are very useful ones. So this is more about the links between density functional theory and mean field theories and Hartree-Fock, where we then use the results from the expectation value of the energy for the electron gas, this so-called exchange term, which, as we will see today when we wrap up the results from yesterday, is something which we can express as a function of the density of the system. So let's just try to collect first what we did yesterday with electron gas, so that we have everything together. And then when we have these expressions, we are going to switch over to a rough description of density functional theory. And when I discuss density functional theory, I will just state the theorems, because the theorems, there are two basic theorems in the density functional theory. And these are also discussed in the course which you guys are taking on density functional theory. So I won't go through the proofs of these theorems, but you can find them in the slides here. But I will focus more on the practical connection between Hartree-Fock theory and how you could actually run a density functional theory calculation. So let's try to do that. And that's why the electron gas is such an interesting result, because it provides the first approximation to the way you solve the so-called Kohn-Sham equations, which are the equivalent, in a certain sense, to the Hartree-Fock equations. So let me switch back to the whiteboard, and then we're going to collect what we did yesterday for the electron gas. So in the calculations yesterday, what we did was to calculate the expectation value of the Hamiltonian. So we wanted, and I'm going to write this in a compact form. So we calculated the expectation value of the two-body Hamiltonian for the electron gas in 3 dimensions. And I'm just going to use this shorthand notation. And that was the expectation value of the kinetic energy plus this interaction piece, HI here. And what we found for the kinetic energy, so let's just quickly look back at that one. So for the kinetic energy, we found that that could be written as the volume of the system times h squared multiplied with kf to the power of 4. And then we had pi squared 10 times m here. And then the other term which we calculated was a term which came from the two-body interaction. Now, it's pretty common to rewrite these terms using the Bohr radius and the radius of a sphere, which represents the volume each electron occupies. And what you will often see is that these quantities are then rewritten in terms of the Bohr radius of h squared divided by 2m electron charge squared. And then we also define a quantity which is called 1 Rydberg, which is the same as the mass charge cubed, no, to the power of 4 divided by h bar squared. And when you convert that one into energies, this is the same as the energy of the ground state of the hydrogen atom. So this is a kind of unit when you scale the equations, which is pretty common in atomic physics and in condensed matter physics when you're looking at electronic degrees of freedom. And then often the energies you're interested in are energies which are expressed in the units of electron volts. So that's a pretty common way of rewriting terms. So what happens then is that we can rewrite this one when we also use the fact that, as we discussed yesterday, we could then rewrite the density, which I will label with rho, in terms of n divided by v, the number of particles divided by the volume. And we found that that could be written as kf cubed divided by 3 pi squared, which we again rewrote in terms of this radius of a sphere whose volume represents the volume which an electron occupies. So this Rs is a typical quantity which you will find in the literature when we express the expression for the energy of the electron here. So if I plug in these constants, what I can do then when I do that is that the kinetic energy, I can rewrite that when I plug this in, and this will be part of the exercise next week, so that you just get some practice with doing this. So what we would get then is something which looks like, when we plug in numbers, it's going to be given by number of electrons multiplied by a constant 221, and this contains A0 divided by Rs. This is just a constant multiplied with 1 Rydberg. So you have these constants. So A0 divided by Rs is just a constant ratio between the two radii. And then this is expressed in terms of 1 Rydberg, which is the same as 13.6 electron volts. So this is just a rewrite of the equations in terms of these different constants. So in the exercise next week, what you will have to do is actually to rewrite the expressions, derive these expressions, and then rewrite them in this specific way, because that's often the way you will see this tabulated in the literature. Okay, now the other quantity which we looked at yesterday, which was more tricky, was actually the calculation of the expectation value of h of I. Now the expectation value of h of I is an exercise in integral calculus, and one of the expressions which we needed to calculate yesterday, and let me just quickly remind you of that, was an integral. So let me just put dots in here and then remind you quickly of one of the intermediate steps which we did. So we had an integral which went like 8 pi, and yesterday we just set up the final answer, but we didn't go through all the details, so I just wanted to repeat this. So this goes up to kf, and this is an integral over dk. And then when we use these Legendre polynomials, we could rewrite this one in terms of factor k divided by p, multiply to the power of 2l plus 2, and then we had 1 divided by 2l plus 1. Now the integral over k is something which we can perform, and when we perform that integral, we can also perform the integral over p, which goes up to kf. And this is a quantity which we can actually rewrite, because we know also what this sum looks like when we have performed the integration. So we will get an 8 pi squared, and then we have a kf to the power of 4, and then we have a sum over L, and then we get a 1 over 2L plus 1. And this factor of 2L plus 3 comes from the integration over K. So when you integrate over K, you get a factor 1 over 2L plus 3. And then K is integrated up to P, and that means that you have P divided by P when you set in the limits, and then you perform the integral over P, and that gives you a factor of Kf to the power of 4. And then there are different factors which cancel out here. So when you now look at this specific sum here, and this is the one which we just set up the answer of yesterday, this is something you would rewrite as a 2L plus 1 over 2L plus 3 And you can rewrite that one as 1/2. So it's actually not so difficult to see it, of 2L plus 1 minus 1 over 2L plus 3. So if you just perform the addition, the subtraction of these two terms, you will get back the previous one. And these are quantities which we can sum up. So when we sum up these, if we rewrite it as a sum from 1/2 plus 1/2, and then we have a sum from L equals 0 to infinity. So the sum runs up to infinity. Then we have a two sums, 1 over 2L plus 3 minus 1 over, so this is 2L plus, yeah. So I'm just changing the limits here. So I get 1 over 2L plus 3 over 2L plus 3 here. So the first sum is a sum which I rewrite by putting out one of the terms, and then I just relabel it. And so you see that the two last terms cancel each other, and this is the same as 1/2 here. So the only thing I did was to take the first sum here and just sort out one term with L equal, when L is equal to 0, because then I have a term of 1/2. And then I relabel my summation indices. And then I get two terms which are the same, and that gives me simply 1/2. So after this to the fourth, when we collect everything, then what we get when we collect it is that this expectation value of the interaction piece is something which ends up looking like minus E squared times V, and then I have KF to the power of 4 divided by 4 pi when I collect all terms here. Now, this is a term which we then can rewrite in using these quantities, which we defined earlier. So if we use this Bohr radius A0 and RS, then we can rewrite this one in the same units which we had with these Rydberg units, and that becomes equal to 0.916 of A0 divided by RS, multiplied with the number of particles and multiplied with 1 Rydberg. So that's the unit which we have. If I then calculate the energy per particle, so the expectation value of the system per particle, then this is something which becomes equal to 2.21, and then it's divided by RS divided by A0 to the power of 2, and these are just constants. So that's a ratio between two radii. So these are just dimensionless quantities when you take the ratios. And then I have minus 0.916 divided by RS and A0. And this is in the units of 1 Rydberg. So the thing which is interesting now, if you look back at the expression which we had here, if you look at this one, this expression here is something which I now can rewrite, this H1 here. We can rewrite that in terms of the density of particles. So if I take 1 over n, this is the same as minus E squared, but now I have the inverse, so it's rho minus 1. Remember now that rho is n divided by V. I have a volume here, so this is just the opposite. So I have rho, and then I have the constants which are given by Kf to the power of 4 divided by this constants which we have 4 pi cubed. And now I can actually rewrite that one. Since I have a Kf here, if we go back and look at the expression we have for the density, so using this expression here, I can actually rewrite what I have here as a function of density. So you see now I have a Kf to the power of 3, which relates to the density. And in this expression here, I have Kf to the power of 4, which should actually be density to the power of 4 divided by 3 times some constants. And then I have density to the power of minus 1. So I will get density to the power of 1 multiplied with density to the power of 4/3 times some constants. So I'm just going to collect all these quantities here in just a constant. So we can rewrite this term here when we now take it as a function of the energy per particle, because at the end, we want to take the limit of the energy as a function of the number of particles when that goes to infinity. So the energy per particle, the energy itself is a so-called extensive quantity. So extensive means that it is proportional with the number of particles. So when you increase the number of particles, and the electron gas is a system where we assume that we have an infinity of electrons. Another system which is similar to this one would be the nuclear matter, which you have in a neutron star. And typical estimation for a neutron star is that you have 10 to the 57 neutrons and protons. And 10 to the 57 is something which we can safely assume is infinity. So if you were to calculate the total energy, you would actually have something which multiplies with the number of particles. If you take then the ratio of the energy divided by the number of particles, the total energy, then you should have something which is constant in the limit n goes to infinity. And this is why you will often see these expressions for an infinite system being expressed in terms of the energy per particle. So that's a pretty common thing to do. So if we do that, if we look at this expression and we just frame that in, so we take this one, we can write this one as a constant multiplied with density to the power of 1/3. And you see, because this quantity which you have here is going to be proportional to density to the power of 4/3. And then you have density to the power of -1. So that gives you density to the power of 1/3. And this is the classical expression which is used in density functional theory. So this approximation here is in density functional theory is called the local density approximation, because we are assuming now that the energy which you get from the exchange term depends only on the density and not on variations around that density. So we're assuming then that the gradients of the density are equal to 0, or the energy as a function of the gradients is equal to 0. And that's why this is normally called a local density approximation, which we are coming back to. So that leads to what's called a local density approximation. For the exchange energy. And we are coming back to the way we're going to use that one a little bit later. Now, there are some small things which are interesting for us as well. And these are things which we will discuss in the exercise next week, because you can, with the energy per particle, you can then define the pressure. And that pressure, if you go back to statistical mechanics, the pressure is then given by the energy as a function of the volume here. So it's the partial derivative of the energy with respect to the volume. So we have now an energy for the ground state of the system, and we are going to put a 0 here. So this is E0, and in our case, this is Hartree-Fock. So our Hartree-Fock energy is now given by this kinetic energy term, which we have, which I just write like this, which we listed previously, minus this constant times something which is proportional to density to the power of 1/3. This is the pressure of the system. And for the electron gas, you can actually calculate an analytical expression for that if you stay at the level of Hartree-Fock theory. And then you can make interpretation of about the stability of the system. So this will be the first derivative with respect to volume. And then there is another thermodynamical quantity which is extremely useful, and that is the bulk modulus, which then is proportional to the second derivative of the energy. It's actually given by minus the volume, and then we have the pressure, and then dV as a function of a constant number of particles. And you see this one is proportional to the second derivative of the energy. So if you have a convex function, and you're at the bottom of that one, you can actually say something about how the system will change under changing pressure, and whether the system is stable or not. And these are considerations which we will discuss in the exercises next week. But we will leave that for the exercise sessions. So in the exercises next week, there will be more interpretations of these results, and also you going through some of the calculations. It's useful to have seen this, because this is a system which allows us to make a nice interpretation about the physics of an infinite system. Now, what I want to do now is actually to move on to the topic, which is not going to be a main topic in this course, but it's going to be a kind of side remark for this, the rest of this lecture and the next lecture. And we want just to link these calculations with the density functional theory. So let's just bring up then the next topic, which is density functional theory. And when we do that, I just wanted to remind you of some quantities you may have seen. So what I will do is actually to bring up the slides which we have this week. So let me do that. And let me share the screen again. So I should have that one. That should be here. So let me just do a full screen. So in these slides, in the beginning, I put up some references. There's actually a typo here. It should be 1T. I saw that now first. Okay. Okay. So you can go through these references. So what Hornberg and Kuhn proved, that we can now express the total energy of the system for, let's say, a system of electrons, or this could just be a system of fermions, of other types of particles. You can use the same formalism for systems of protons and neutrons in dense nuclear matter, except that in that case, you don't have a static external potential, which in our case could be an atomic nucleus, if that's the case, or it could be the background charge from the ions in the electron gas. We can actually show, what they showed is that there exists a unique functional, which is a functional of the density of the system. And the minimum value of the total energy functional is the ground state energy of the system. And in case of electrons, this charge density, which is the same as the density of particles multiplied with the charge. That's the definition of the charge density. So that charge density, which yields this minimum, is then the exact single particle ground state energy. So in Hartree-Fock theory, you work with typically large basis sets when you're doing that. And that often poses a problem for large systems. And an alternative is normally DFT. And DFT takes into account electron correlations, but is normally less demanding computationally than, let's say, full-scale diagonalization, copper cluster theory, or any many-body theories, any other many-body theory. And density functional theory is the method of choice if you're doing material science. It is the method of choice if you're dealing with large systems. Before the systems become too large, that you have to freeze out the quantum mechanical degrees of freedom and create an effective potential, which you then would use to do molecular dynamics calculations. So there is a kind of hierarchy in many-body physics. So where you would have the full microscopic calculation, like FCI, but you are clearly limited due to the exploding degrees of freedom. You can rephrase everything in terms of a mean field theory. So Hartree-Fock is an example of that. But Hartree-Fock theory is defined in terms of the single particle basis which you have, which can become very large when you look at the number of states above the Fermi level. And in many cases, you may perhaps have a huge basis set, and that can typically complicate Hartree-Fock calculations, because you would use that basis set to calculate effective matrix elements of the two-body type, perhaps three-body type, and more complicated ones. So Hartree-Fock calculations can become expensive as well when you have a huge single particle basis. So mean field theories like density functional theory, which actually are based on an exact theorem, an exact relation between the density of the system and the energy, these can provide a practical recipe for dealing with systems with many degrees of freedom. But then that type of approach also meets its brink. So when you are dealing with something like 10,000 particles, then density functional theory starts to meet its own limitations. And that's when you typically will switch over to molecular dynamics. I don't know if you're familiar with molecular dynamics, but think of atoms in a lattice, and you have zillions of these atoms. So what you would do then is that you would freeze out the quantum mechanical degrees of freedom, and you would produce effective classical potentials between the ions in a lattice. So this is a classical potential which has supposedly some quantum mechanical degrees of freedom baked in. And then you would simply solve a system of coupled differential equations using Newton's law of motion. And this is something you can solve for millions of ions, but then you've frozen out the quantum mechanical degrees of freedom and you have an effective potential. There's actually a huge field of research linking, let's say, the fully microscopic description with mean field theories, density functional theories, and then molecular dynamics. So depending on the degrees of freedom we have, some degrees of freedom may be less relevant and others may be more important. So if you have a big material and nothing happens, you may even model this one using Newtonian mechanics or solving partial differential equations. But then suddenly in this big system, there starts to appear a crack. Suppose the window in your car, you start getting a crack in your window. And then you have chemical reactions in the crack here, which can become important for the property of the glass or the window. And maybe you would have to model these properties with density functional theory. Or perhaps you have to go down to the microscopic approach with, so a density functional theory was also microscopic theory, but you freeze out some degrees of freedom in the exchange potential, as we will see later. So when I say fully microscopic, I mean you use all the degrees of freedom and you let the particles interact through the many-body interactions which you have present. And then you would typically solve FCI, use FCI as a method, or you would use Monte Carlo calculations, but these are quickly limited by the exploding degrees of freedom. So there's a kind of hierarchy where you have specific degrees of freedom you would freeze out. So like me, who does nuclear physics, I would not deal with quarks because that would not allow me to do any kind of practical calculations for a nucleus like lead, which has 208 protons and neutrons. This is really at the brink where you can run calculations of the type of copper cluster theory or Monte Carlo calculations, etc. Then when you get to larger systems, then you want to have effective one-body equations which you solve. And these single particle states can then define a density of states, which we are coming back to now. And then the density, the charge density of the system. So let me bring up some of these quantities. You may have seen them. So a quantity which is called the one-body density is defined in the coordinate space in this way here. You may have seen that one. And that just relates to of the likelihood of where you can find a particle in a specific medium here. So these RIs would be the positions of all the other particles. And in second quantization, this is something you would write out as a one-body operator. And where this rho alpha beta is simply given by this quantity here. Then, when you now look at the number of particles in this system, since the number of particles is n, and the integral of the expectation value of this one-body density operator, that should give you n particles. So with appropriate similarity transformation, you can make this operator diagonal in the single particle basis psi alpha. So if that operator is diagonal, then you would have a density which is described in this specific way. And if you have now a many-body state like this is your many-body state. And we know that that can be a linear combination of Slater determinants, or there can just be one Slater determinant. And remember now that the Slater determinant is just given as the product of these operators. Then, if you then take the expectation value with a given Slater determinant for this specific operator, if you take the ground state, for instance, that should give you the number of particles. So that means that if I look at this quantity here, this is the same now. And when I take this chain of Slater determinants, it's now going to be given by these coefficients. And if I have only one, this just reduces to one. So this is the number of Slater determinants I'm summing over. And the overlap between these Slater determinants in the exact wave function. If my wave function from a Hartree-Fock calculation, which we know is just one Slater determinant, then this psi0 would be your Hartree-Fock wave function. And your Hartree-Fock wave function would then simply imply that what you're calculating is this expectation value when you integrate over R. So this is a one body density. And when I integrate over all of space, then this should simply give me the number of particles. So this is a typical test which you will have when you introduce the density. And instead of varying the single particle wave function, we are now using the Hohenberg-Kohn theorems, where we state that the energy is now a function of the density. So instead of minimizing the energy with respect to the single particle states, which we did in Hartree-Fock and which we did in FCI, we are now going to vary it with respect to the density. So this, you can also do that one. Also, I wanted to bring in a small intermezzo here, which is useful if you're going to solve Hartree-Fock equations or the Kohn-Sham equations for the single particle orbitals. So when you look back at the Hartree-Fock Hamiltonian, which we defined for two states alpha and beta, with the computational basis we have used, then this is given by these coefficients which we get by solving the Hartree-Fock equations. And normally we assume that the basis we have start with is a basis which is diagonal in this H0. It could be hydrogen atom, or the harmonic oscillator or whatever. And then what's common to do then when we have the equations here is actually to rewrite them in terms of the density matrix. And the density matrix is simply given by the sum over these coefficients as a function of number of particles. And that means that if you go back to the sum you have here, this specific sum, you can single out the sum over J and calculate the density matrix, this quantity here, and just plug that one in here in each calculation. So instead of having a triple sum, you have just a double sum. When you solve the Hartree-Fock equations, you have these coefficients, and you can then calculate the density matrix, and then you would simply pre-calculate this quantity, and you would reuse that one in the calculation of the Hartree-Fock Hamiltonian. This is a kind of a trick, or not exactly trick, but it would be the more efficient ways of running the calculations when you do both a Hartree-Fock calculation and a density functional theory calculation. So with the Kohn-Sham equations, what we are going to discuss pretty soon after we've stated the theorems is actually the expression for the energy here, and that leads to a set of equations. So the ground state, if I have a single Slater determinant, which is my optimal one defined by the single particle states, then I can define the density, the ground state charge density, in terms of the sum over the single particle wave function squared. So this sum is over what we will call the Kohn-Sham orbitals. But if you have a Hartree-Fock basis, then this rho Hartree-Fock would simply be the sum over the single particle wave functions from the Hartree-Fock calculation, which define your Slater determinant. This is going to be one of the exercises next week as well. So where you actually will show this type of expressions so that you get some feeling with how you get there. So now I'm just using you, I'm just stating that this is what you get when you take a single Slater determinant and you calculate the density, the charge density. So I put the charge equal to 1, and that's why the charge doesn't come into the equations here. Just keep that in mind, eh? So I'm using these natural units when it suits me best. And if you don't see the constants, which is often common, it could also be because I've forgotten to write them. And then I can just invoke natural units, which is a very, say, irritating thing. I don't know how many times I've just spent on retracing where to place the constants back again to get the right units and right dimensions. So that's always, you will always see that in textbooks. We use natural units, and then we put E equal to 1, H bar equal to 1, the mass is equal to 1, and then you have to figure out where to put them back again when you want the expressions in specific units. So here, I call this the charge density, but I put the charge equal to 1. So the thing is that this quantity here can then be used to define uniquely the ground state of the system. And we can have an energy which is now expressed in terms of the density. And that's the quantity we're going to vary. So I will bring up these things here after the break here. So let's now go back to the to this whiteboard and bring up the equations which we need to look at. Oops, here we are. So if we look at the density functional theory, what we are going to have now is a set of equations. And we are going to derive these equations. So the type of equations we are going to have now is a equation where we have the kinetic energy, and I write this as T of R. And what I'm going to do now is just to skip spin degrees of freedom, if that is okay. So I'm just leaving that out. So if you have spin in addition, you would have to insert that. So I'm just looking at the spatial degrees of freedom. And then there is a external potential, which could be the potential which confines the motion of the objects. And this could be a harmonic oscillator, it could be a Coulomb type of potential, or as in the electron gas, there is no external potential. Or rather, there is an external potential, but that comes from the background ions, which gets cancelled from the direct term in the correlation energy for the electrons. So there's an external potential, and then there is a new term, which we are going to bring up here, which we are going to have as a function, which is proportional to the density. So there's a d of r, and then I have my density, and I'm going to define this density just in a moment. So this is primed. It now contains an interaction piece. So it's time, an interaction, which I just leave undefined. So that's an integral. And then there is an exchange term, the exchange, which now depends on the density. And it's also a function of this r. And this gets multiplied with psi of k as a function of r. And that's going to give us the energy. So this is a lookalike of the Hartree-Fock equations, so which I just want to bring up now. So we see the kind of similarities. And we are going to derive this equation, which you see here. And this is going to be given by a energy, epsilon k, and I put a ks here, and this stands for Korn-Sham, multiplied with psi of k of r. And these are the solutions to Korn-Sham equations. If you think back to Hartree-Fock theory, so let's try to see the similarities here. What we had in Hartree-Fock theory was the kinetic energy. So these are the Hartree-Fock equations in coordinate space. So we had an external potential of R, and then we had a so-called Hartree potential. So let me just write this out here, of R. And this gets multiplied with a wave function, psi of k of R. And then there was an additional term of a d of R prime. And this had the u, this is the Fock term. I have to be careful here. And then this is multiplied with psi of k, but now with an R prime dependence. And this is equal to this epsilon k of Hartree-Fock multiplied with a wave function for the Hartree-Fock case. So we should put a ks on this one, and an hf on this function here, and an hf here. So these are the Hartree-Fock functions. And this u Hartree is a direct term, and that term is given by the following expression, which is now a sum over all the states below the Fermi level. And I have an integral over d of r prime. And then what I have is the wave function I prime squared and multiplied with a potential. Now, one of the things you will show in one of the exercises, so this psi of i's here are Hartree-Fock wave functions, and I'm going to drop the superscript Hartree-Fock in the wave functions just for notational simplicity. But keep in mind that the wave functions you're seeing here and here, they are different in principle. So if you look at this specific term here, we can actually rewrite that one if we now use, and this is one of the exercises next week, that if I have a Hartree-Fock Slater determinant, you can then show that the density matrix, or the charge density, is given by I equal 1 up to the number of particles, which is the same as summing up the all the states below the Fermi level. So if you look at this expression which you have here, this one, this is the same as we have in the sum here and here. So I can actually rewrite my Hartree term. So if I use this one, this can be rewritten as an integral over d of r prime, rho of r prime, multiplied with a potential, like this. So my Hartree term is something which I can rewrite in terms of the charge density. So if you look now at the Kohn-Sham equations, what you have is a term here, the second term which we have, this one, which is actually the same as the one we would get from Hartree-Fock theory, except that the single particle wave functions are different. So let me just bring up one final thing before we take a break. And let me just remind you of this U, the exchange term. I actually never dare to pronounce the name of this Russian physicist. So I like to call this the exchange term. It's, yeah, you understand why. So that one is going to be given by a sum over, there's a minus sign, I less than F below the Fermi level. And then I have a psi of I, complex conjugate, and this depends on R prime. And then there is a term V of R, the potential energy, multiplied with psi of K of R. But note that this term here is actually inserted into an integral, as you can see here. And this is the exchange term. So this is our exchange term. And we cannot write it, so note this, cannot write it as something proportional to density. So this brings in a nonlinearity, which we then are going to use when we do density functional theory. This exchange term is going to include all the complicated many-body physics, which we cannot express in the direct term or the Hartree term. So the whole idea is that there is a unique determinant for the ground state. And that unique determinant defines then a density. And that unique determinant allows us then to find a single particle basis. But the problem with that single particle basis is that if we now have it, we may not, or if we have an ansatz to it, we may not know exactly what this one is going to look like. So that's the main problem with density functional theory. And that's where all the research is actually going into, to find a better and better approximation to the exchange path, given a Slater determinant. So if I take, and this is one of the exercises next week, let me just put that in a box here. If I calculate the expectation value of a Slater determinant, phi 0, of this operator rho of r, what you will find is that this is given by the sum of all the single particle energies, which define this Slater determinant. So these are single particle wave functions. So that's, if somebody is able to define a one-body density, or a charge density, as the expectation value of a unique Slater determinant, or determinant which represents the ground state of the system, then you can express the charge density as a sum of these single particle states. So with a Hartree-Fock basis, this follows automatically, but you know that the Hartree-Fock solution is not the exact solution to the ground state of the system. It's an approximation. So in a way, what we are doing now is to introduce an optimization problem where we assume that there exists such a unique density. And this is one of the theorems by Hohenberg and Kohn, where I actually show that there exists such a unique density. But we don't know what it is. And that is basically, so in a certain sense, it's a very fundamental theorem on many-body systems. But the problem is that we don't know what this density is, because if we have it, we've solved the problem. Should we take a small break? Is that okay with everybody? I went a little bit over time, so I just put the recording on pause here. Do that. So before the break, we set up the equations for the so-called Kohn-Sham equations, which define an effective type of single particle lookalike equations, which are very similar to the Hartree-Fock equations. So the exception is now that, or the difference is that we have this exchange term, which replaces the exchange term we have in Hartree-Fock theory. So if we go back to Hartree-Fock theory, we have this term, which we call the Fock term, this term here, which gives a rise to a non-linear equation in the unknown quantities. And then we have the direct term, which is normally called the Hartree term. And the thing now is that we are going to have an equation which is pretty close to the same equation, but now this exchange term is going now to introduce complicated many-body correlations, which we do not have in Hartree-Fock theory. So you can think of Hartree-Fock theory as a single particle equation where we have the interaction to first order in the interaction, because the interaction just appears in the direct term and the exchange term. So this is also a type of many-body correlations. So the exchange term represents correlations due to the Pauli principle. Now, when you include more complicated contributions, as you will see in many-body perturbation theory, there is a very systematic way of including more complicated contributions. When you diagonalize, for instance, in the FCI calculations, you include these contributions to infinite order. So perturbation theory is just you trying to construct what a full diagonalization does, order by order. So what we are trying to do now is to bake in all the unknown physics into this exchange potential. And the assumption is, which is actually not an assumption, it's a theorem, which says that there is such a unique density, and that density defines then a unique ground state representation. And with that, we can then find an effective one-body type of interaction. So if we now look at the energy which we had when we had just one Slater determinant. So let me just remind you of the total energy. So the total energy of the system with just one Slater determinant with an SD, and let's just call this for simplicity phi 0. And this phi 0 is given in second quantization in terms of all these operators, AI acting on a true vacuum. And then alternatively, this is given in terms of a Slater determinant when we're looking at the first quantization or just the coordinate space representation. And then we have a factorial, n factorial, and then we have all these single particle states where we have orbit 1, and then we have a psi 2 of R1, and this goes down all to psi of n of R1. And these are the states which we fill up to the Fermi level. And we have a psi of n of Rn. And again, I'm skipping spin degrees of freedom. So for this quantity here, when I calculate this density, the expectation value of the density operator, then that just reduces to the sum over the single particle states. So if we look at the total energy then with a Slater determinant, and we have this basis set here, then the total energy, the expectation value of this phi 0 of h, and keep in mind as well that phi 0 multiplied, or this as an eigenvalue problem, is different from the true eigenvalue multiplied with this quantity. So these phi zeros are not eigenstates of the full Hamiltonian, except if we have taken seriously the Hohenberg-Korn theorem, which states that there exists such a unique Slater determinant as a function of the density. But when we do Hartree-Fock theory, this is not the case. So when we do this and we have this Slater determinant, so this is irrespective of whether we have done Hartree-Fock theory or not, or if we have done Kohn-Sham theory and have a single particle basis. So when we calculate this expectation value, this is, as we have seen before, is given by a summation by the all states below the Fermi level, and plus 1/2, and then we had this double sum ij, and then we have ij v ij minus the exchange term ij of v of j of I. We used to sandwich this into just one term, and we call this the so-called exchange and direct term, but then we used anti-symmetrized matrix elements. So if we now look at the total energy, if we focus more on the terms which come from the exchange part, so this ij here, if we look a little bit closer at it, if we take the first term, which is a direct term, this is actually a sum over ij, all states below the Fermi level, and it's given by an integral over d of r prime. And let me just remind you quickly of the expressions which we calculated earlier in the semester. So we had a j, and then we have an r prime, and this is then multiplied with a potential and multiplied with psi I of r and psi j of r prime. Now, what we see here is that the sum over I here, including this one and that one, can then be rewritten as this density for the variable r, and then the other one can actually be rewritten as a density over this r prime here. So that means that we can rewrite this equation as a 1/2, and then we have an integral over d of r, an integral over d of r prime, and then I have this rho of r prime, multiplied with v of r prime. So the direct term can actually be written out as a function of the densities. And when I take the functional derivative here, since I have two densities, this is going to just give us a factor of 2, which cancels the factor of a half. And then we will have an expression which depends on the density times the interaction. So if you think back, so this is the total energy of the system. So if you think back to the Hartree-Fock equations, what we could do then is actually we could write the Hartree-Fock energy in terms of just the density here. And you will see that when we now take the functional derivative with respect to density, we will get that specific term. Now, the thing which complicates life for us is obviously the exchange term. So the exchange term, when we set up the expression for that one, Ij of Ij V Ji, you can see now that this is something which we cannot split up into something which depends on the densities here. And there is a sum. Let me just correct that one a little bit. And then I have a psi of I, complex conjugate of R, psi of J, complex conjugate of R prime. I have the interaction matrix element. And this is multiplied with psi I, but now with the coordinates R prime, and psi J here with coordinates R. And this is something which I cannot now write out as two densities times interaction and then their integral. So this kind of non-locality is the one which actually causes problems for us. Now, if we also look back at what we did with Hartree-Fock theory, so when we had Hartree-Fock theory, what we had then was that the energy could, this same energy, which we wrote up here, this one, which we can label as E0 Hartree-Fock, we can rewrite that one in terms of the Hartree-Fock energies. And this is something which we can rewrite as a sum over all the single particle energies below the Fermi level. So I have an epsilon I Hartree-Fock minus, and then we had a factor of a half, and then we had this Ij, V, Ij, the direct term, and then plus 1/2, which is the exchange term, Ij, V of Ji. And this is something, again, which we can write out as the Hartree-Fock energy of epsilon I Hartree-Fock minus, and then I have 1/2. And if I now use these expressions which I set up in the previous slide in terms of the densities, so I would have a rho of R, rho of R prime, multiplied with V of R. And then I'm just going to write out a term here plus E Hartree-Fock exchange. And Hartree-Fock exchange is going to be given by this term, which you see here. Like that. Now, when I do density functional theory, then I'm going to have a, term here. I'm going to have an E0 Kohn-Sham, which I can write out as I less than F, but then the energies here will be the Kohn-Sham energies, which are the solution of a different differential equation. And then I'm going to have this minus 1/2, and I'm going to have a term which goes like d of R, and d of R is the same term, and then rho of R prime, multiplied with this V of R prime. And then what we will show soon now is that this can be written out in terms of an exchange energy, which depends on the density, minus another term, which now depends on the integral over d of R, and there is a V exchange, which depends on rho and is a function of R. And this equation here is now defined in terms of this X of C, which is the exchange energy, the exchange correlation energy. Which replaces the term which we had 1/2 Ij in Hartree-Fock theory. The exchange term replaces, which is the exchange term, in Hartree-Fock theory. So this V exchange, which we have set up here, which is a functional of the density and also a function of R, is given by the functional derivative of the energy, of this exchange energy, as a function of rho. Now, what we are going to use now is that this exchange energy is the same as the local density approximation we got from the homogeneous electron gas. So what you end up doing then, instead of optimizing E of psi 0, which we did in Hartree-Fock theory. So this is what we did in Hartree-Fock, which is the same as us having an argument, the set of single particle states, but I'm just going to write this phi 0. And then we optimize this quantity. What we typically end up doing now is to have a different minimization problem where we use the variational calculus. So we would now have an energy which is a function of the density, and then we are going to optimize this quantity here as a function of density, and then we have psi, and I'm going to just mark these wave functions with a psi or phi here. We're going to use the same symbol, but now the wave function is going to be a function of the density. So this is now defined by rho. So the quantity which we now are going to look at, if we think of the non-interacting case, if we look at that one first, what we have then is that the Hamiltonian is just given by kinetic energy plus this V external. And the kinetic energy is just the sum over for all the particles which we have present. And then we would have minus del squared divided by 2 of I. And this V external is just the sum of all these external single particle potentials which we have. So we would have a V external of R of I. So if you look at the non-interacting case, what we are going to assume now is that there is an energy, E of rho, for the non-interacting case, which is simply given by the kinetic energy as a function of this density, plus this term d of r, where we now integrate up all these single particle guys multiplied with rho of r. So if we perform a variation with respect to the density, and we need to have a Lagrangian multiplier as well, so we would then have a variational derivative with respect to density of this quantity, plus the other quantity, which simply gives us this V external of R. And this is equal to some lambda, which is a Lagrange multiplier. It's very similar to what we did as a function as a function where we optimize with respect to changes in the single particle wave functions. When we optimize with respect to the single particle wave functions, we get Hartree-Fock theory. If we now optimize with respect to the density, we are then going to get something which we will call the Cohen-Sharman equations. So in this specific case, we have assumed that even if the form of T rho can be unknown, we know, however, for the non-interacting case, that we can actually define a wave function which consists of single particle wave functions, which are eigenfunctions of T, the kinetic energy, plus the external potential. So just think of a harmonic oscillator. Then we know that we can define exactly the single particle energies, and we can find the single particle energy or the expectation value of the kinetic energy and the expectation value of the harmonic oscillator potential, for instance, as a function of the basis functions. So if we have a case like a non-interacting case like an H0 acting on this single particle basis, we can actually define that. We can solve that uniquely, and we can define a unique Slater determinant, which then would be the eigen state of this H0. So that will have an H0 of phi 0. So this can be uniquely defined. For the interacting case, this is no longer the case. And that's simply because when we have an interacting case, this density which we have here, that is a density which reflects the solution to the full problem. So that means that the expectation value of the kinetic energy will be different when you have, let's say, the exact wave function. So if I calculate the expectation value of the kinetic energy with this function here, which is the solution of that part of the Hamiltonian. So if I have phi 0 of just the kinetic energy operator, which is now the sum over all the single particle kinetic energies, this is different from the one which now is the exact solution of the problem. So where we have assumed now that H acting on this phi 0 is different from the exact energy, which I just labeled with this one. Whereas when I have now H times psi 0, that is the same as the AE times psi 0. So that's the exact energy. So if I calculate these two quantities, they will give different results. Okay, so that sounds obvious, right? So which means also that if I have the exact density, that density there will obviously give me kinetic energy, which depends on density, which is different from the kinetic energy coming from the density defined by this quantity here. So when I have a non-interacting case, then since I have the solution to the problem, then I can define this quantity here, and that is known. But in general, since I don't know this rho, then that dependence for T is unknown. Or it's something we have to solve by approximations. So for the non-interacting case, this is pretty straightforward. But if I then move to the interacting case, then I have to bring back this expectation value of the exchange part, and life is a little bit more complicated. So let's bring up the exchange term, which we are using to replace. So as I said here, this exchange term, which we have here, this one, is now replacing the expectation value of this quantity, which you see here. So let me just bring back my notes here and look at the total energy. I suddenly have to look back at the flow of arguments here. Okay, so what we're going to do now is to define the total Hamiltonian is going to contain the kinetic energy plus this external potential. And then, in addition, then I have my interacting piece, which I write like this H of I here. So when I then define the energy of the system in terms of this density, there's going to be a density dependence for the kinetic energy. There will be a term which now contains this external potential, which is the same as us performing this operation here, where we have V external as a function of R. And then I have my exchange term, now my direct term, which is given by 1/2. And then I have my d of R prime. And then I have the two densities multiplied with V of R prime. And finally, I just bring in this exchange term, which is the unknown term here. So when I then calculate the functional derivatives, so what I'm going to vary then is to vary this equation here, vary with respect to rho, with rho. So what we are going to get then is a variation of T with respect to rho plus this delta E exchange with respect to rho plus, and if I look at the term with the two-body interaction, the direct term here, that's going to give me two derivatives, one here, and then that takes away the factor of 1/2. So I simply get plus d of R prime of rho of R prime multiplied with V of R and R prime. Oops, let me just correct that one. Like this. And then I have my final term here, which is going to be given by delta of EX exchange of delta with respect to the density here. And this is going to be equal to a Lagrangian multiplier multiplied with the density, like this. So this is now my variational calculus, which I'm applying my variational calculus. And this allows us to define some kind of effective potential here. So if I now redefine an effective potential, V effective, then what I have is an external potential plus this delta of the exchange term of delta rho plus this term of d of R prime, rho of R prime multiplied with this term, the potential term. And that means that I can then set up an effective single particle potential equation, an effective single particle equation, which then looks like kinetic energy, depending on R, plus this V effective, this effective potential, which then acts on the single particle state. And this gives us the Kohn-Sham orbitals. And this is equal to epsilon K, the Kohn-Sham energy, times psi of K of Ks. So Ks stands for Kohn-Sham here. So if I then look at the approximation then, which we are going to make here, is that for if we have a non-homogeneous system, when we look at this exchange piece here, the non-homogeneous system, in general, the value of this this energy contribution and its functional derivative. So this quantity here defines actually the potential, this Vx exchange. In general, this Vx of C as a function of density, which is now defined to be the functional derivative of this quantity. This function here is in general a function of the density of rho. But then if I think of variations of the density at a given point R, and we know that this V of x depends on the value of these quantities, the exchange energy and the exchange potential, they depend at a given point R, not only on the value of the density, but also on variations of the density. That means that this function here may depend on high order derivatives of the density. Because we can think of at a given point, it may not depend only on density, but also on variations in the density. And these variations in the densities are then given in terms of these different gradients. So we could write it like this. And this defines also, how to say, the active research in density functional theory and how you actually approximate these different gradients. So this is a big research field. So density functional theory is actually in itself a huge research field where a lot of the research goes into you trying to find approximations beyond what is called local density approximation. So when we say the local density approximation, what we are assuming then is the following. So in that specific case, we assume that V, this exchange piece here of rho of R, is just a function of rho of R. So there is no variation in the density. So that means local density approximation. Because you could think that the density could vary as well around a point P, a point R. And if it varies, then the dependence on the gradients is something which will also characterize this exchange potential. But now we're simply assuming that there is no variation in the density at a given point R. And if we do that, we have the so-called local approximation. And this local approximation now, if we look at the total energy, this is given by an integral over a quantity which I'm going to call epsilon exchange of rho of R multiplied with rho of R. And this xc of rho, that is called the exchange correlation energy, which is then used where we would typically use the results from the homogeneous electron gas. And we know that that one is proportional to 1 over rho to 1/3 as a function of R. So now we are using the result from the homogeneous electron gas, where we actually have assumed that we have a local density approximation. If we then plug that into the expressions which we have, we see easily now that this E exchange is now given by minus. So this is a minus actually, minus, and then we have a constant. And then we have an integral over d of R. And then we have the density to the power of 4/3 because we have the density here as well. And you remember now that the total energy before we looked at the energy per particle was actually given by the density to the power of 4/3. So the potential which we are looking after, this effective single particle potentials, this delta, or this Vx of c then, which is given by this quantity here, delta rho, that gives us simply minus 4/3 times a constant and multiplied with rho of 1/3. And then we can obviously redefine this as a new constant, minus constant of rho 1/3, where we just absorb that term 4/3, which comes from the functional derivative. And that means that I can now rewrite my Kohn-Sham equations in terms of the kinetic energy operator, T of R. I have this external potential, which confines the motion of the particles. I have my direct term, which is simply given by d of r, and then I have the density, rho of r, multiplied, so this is a rho of r prime, multiplied with v of r and r prime, plus, or actually minus, this term which goes like a constant, times rho of 1/3 of r prime, sorry, r, not r prime, but r here, and multiplied with psi of k of r, and this is giving us the epsilon k Kohn-Sham multiplied with psi of k of r here. And this defines the final equations which you end up solving. When you use the local density approximation, which then is given by the, can be given by the results which you have from the homogeneous electron gas, which then depends on the density to the power of 1/3. And if you use that one, then you have an efficient way to set up your single particle wave functions. But you see clearly that this is going to give us something which may not be as good as the Hartree-Fock solutions. So actually, if I run calculations for different atomic systems with the Hartree-Fock approach, and with this approach where I replace the exchange term from the Pauli principle with just the exchange term for the homogeneous electron gas, I will actually get total energies which are above the Hartree-Fock energy. So for simple atomic systems, if I were to run it for the helium atom, for the neon atom, etc. But then in research in density functional theory, there are tons of different approximations which try to improve upon this starting point. But you see now that you have, if you have a Hartree-Fock machinery set up, then you can actually redefine your Hartree-Fock Hamiltonian in terms of this specific Hamiltonian. So if you look back at the equations which we had earlier, let me just bring them up here in the slides here. So if we go back to the Hartree-Fock equations, where did that end up? Here we are. So if I go back to my Hartree-Fock equations, what we could do now, when you look at the Hartree-Fock Hamiltonian, because here we're dealing with anti-symmetrized matrix elements, we would then have a direct term, which is as before. But then instead of the exchange term, which we would have here, we would simply plug in the local density approximation. And that depends just on this single particle wave function squared. So this is a much simpler approach to the exchange part than in Hartree-Fock theory. But in principle then, we would actually set up, instead of having Hartree-Fock here, we could replace this with Kohn-Sham and local density approximation. But the type of equation we would be solving would essentially be the same type of equations here. There is nothing different except by the way we treat the exchange part. But then this is just the beginning of the DFT story. So these things were derived back in the early 60s. And I think this was done back in 64, something like 1964, 1963. And so we have roughly 60 years of developments beyond that. So here, as I said, as I told you, I just wanted to use density functional theory as a way to link that with Hartree-Fock theory and the many-body methods we are discussing here. And at the same time, it allows me to extend the academic usefulness of the electron gas calculations. And the electron gas is one of these few systems where we have analytical solutions for the single particle energies and the expectation value of the ground state. And that allows us also to gain insights about the many-body physics due to the Coulomb interaction. And it serves also as a good starting point for making comparisons with experimental data. And it has been very successful in studying properties of metals. So for those of you coming from solid state physics, this is a system which you probably have seen in different types of courses. And when you take a course on density functional theory, one often just says that we use a local density approximation. And it's not always derived in different courses, but it comes from the electron gas. So this kind of detail which we took, hopefully you find it interesting because it links well with a huge research field in density functional theory. And at the same time, it allows us to gain insights about correlations in many-body physics. So when we move to many-body perturbation theory, we can actually improve upon the Hartree-Fock calculations by doing many-body perturbation theory or other types of many-body methods. So this is where I'm going to stop today. And next week, we will start with many-body perturbation theory. And since there was a wish for doing Green's function theory instead of copper cluster theory, we will end the semester with Green's functions after we've done many-body perturbation theory. Because Green's functions are often best understood if we have done many-body perturbation theory first. And that's where we will end the semester. Okay, guys, any questions? Okay, and it's just best wishes for the weekend. And for those of you who want to do the exercises, Spian is going to be here pretty soon here.